Welcome to The Explainer. I am absolutely thrilled you're joining us today. We are going to dive straight into one of the most mind-bending, awe-inspiring engineering challenges on the planet, manufacturing the world's largest telescope mirrors. If you've ever looked up at the stars and wondered, how exactly humanity manages to capture the incredibly faint light from the very dawn of the universe? Well, the answer lies in pieces of glass that are so unbelievably massive, they completely defy traditional manufacturing. So today, we're going to put together a beginner-friendly guide to exactly how they pull this off, breaking down some seriously complex science into a straightforward step-by-step recipe.
So, let's confront the sheer unimaginable scale of what we're actually talking about here. How do you build a mirror the size of a building? Imagine trying to create a single, continuous optical surface that is 25 meters across. That is roughly the size of an 8-story building laid completely flat on the ground. You obviously can't just pour a sheet of glass that big, strap it to a truck, and drive it up a mountain. It simply wouldn't survive the trip. But to build the next generation of astronomical observatories, like the giant Magellan Telescope, we need mirrors of exactly this monumental size. So how on earth do we do it? Here's our roadmap for today. We're going to cover 1. The giant mirror problem. 2. Lighter, stronger, smarter designs. 3. The spin casting recipe. 4. Annealing, the big kill. And finally, 5. Polishing to perfection. All right, Section 1, the giant mirror problem, and exactly why big glass fails.
For decades, simply pouring a massive, solid piece of glass was basically doomed to fail. And it all comes down to basic physics. If you make a solid glass mirror that massive, it becomes incredibly heavy. So heavy, in fact, that gravity actually causes the glass to physically sag and deform under its own weight, which completely ruins the focus of the starlight. And on top of that, a massive block of solid glass stores an enormous amount of heat. As that heat slowly escapes into the cool night air, it creates the shimmering effect, kind of like the heat waves you see rising off hot asphalt in the middle of summer. And that shimmering distorts the images of the universe. So the brilliant modern solution to both the weight and the heat? The honeycomb mirror.
Moving on to Section 2, lighter, stronger, smarter designs. We'll look at segmented and hollow solutions. One really clever strategy to bypass the limits of solid glass is segmentation. Think about telescopes that hunt for incredibly fast, invisible flashes of radiation in our atmosphere. Instead of one giant, heavy mirror, they use a whole bunch of smaller, hexagonal mirrors linked together. It's like a giant puzzle, and it solves multiple problems at once. First off, smaller mirrors don't sag. Second, these little pieces can sit on platforms that move independently. So if the wind blows and the telescope shakes, the mirrors just instantly adjust to stay perfectly pointed. They're also super light, which lets the telescope whip around quickly to catch fast astronomical events. And if one breaks, hey, it's infinitely cheaper and easier to swap out one small hexagon than an entire monolithic mirror. But what if you still absolutely need a massive, continuous piece of glass, like the 8.4-meter segments they use for the giant Magellan Telescope? Well, the answer is the honeycomb structure. You can think of this literally just like a beehive. By leaving the inside of the mirror almost entirely hollow, you keep all the structural stiffness of a thick piece of glass, but it becomes amazingly lightweight. And the best part? Because it's mostly hollow air inside, it cools down extremely fast, which completely eliminates that annoying image-ruining shimmering effect we talked about earlier. Section 3, the spin casting recipe. This is how you go about cooking a massive mirror.
Okay, to capture starlight, a telescope mirror can't just be perfectly flat. It has to be curved, like a shallow bowl, to focus the incoming light. Now, instead of grinding that deep bowl shape entirely by hand, engineers melt the glass inside a giant furnace that physically spins around like a carnival ride. Just picture a bucket of water. When you spin the bucket in a circle, the water naturally climbs up the outer edges, right? Spin casting uses that exact same centrifugal force to push the molten glass outward, naturally creating a perfect parabolic curve. Let's break down exactly how this happens. If you were casting a mirror out of bronze using ancient techniques, you'd make a sand mold with a complex plumbing system of channels for the liquid metal to flow into. Glass doesn't work like that. Here, engineers build a massive tub and install about 1,700 hexagonal boxes made of ceramic fiber. Then, they carefully load pristine chunks of raw, heat-resistant borosilicate glass, which is actually super similar to the Pyrex you might have in your kitchen, right on top of those boxes. They seal up the furnace and blast it to 1,200 degrees Celsius. The glass doesn't turn into a watery liquid, it actually reaches a consistency like thick, cold honey. Over a few hours, it slowly oozes down into the tiny 12-millimeter gaps between those 1,700 boxes, all while the whole furnace is spinning to give us that beautiful curve.
Once the glass cools down enough to be handled safely, a massive steel lifting fixture grabs the entire 40-ton structure and turns it completely vertical. Technicians then take high-pressure water and just blast out all 1,700 of those ceramic fiber boxes from the back. What you're left with is a giant mirror that is structurally rock solid, but magically 80% hollow air. They literally wash away 20 tons of mold material in just a couple of weeks. It completely solves the weight problem. Section 4. Annealing. The big chill. Locking atoms in place forever.
Actually, let's hit pause, because we kind of skipped over a wildly dangerous step in that cooling process. This is where annealing comes in, and it is the absolute ultimate test of patience. Think about baking a delicate soufflé, or a cake. If you pull it out of a hot oven and instantly stick it in the freezing cold, that extreme temperature shock will ruin it, right? It'll just collapse. Glass is exactly the same way. If you try to cool 20 tons of molten glass too quickly, the internal stresses will build up and cause the entire multi-million-dollar mirror to violently shatter into a million pieces. To stop that nightmare scenario, the temperature inside the furnace is lowered by a mind-bendingly slow 3 degrees Celsius per day. Just think about that. 3 degrees a day. The whole cooling process takes 3 agonizing months to finish. But that extreme patience is absolutely crucial. It allows the atoms in the glass to gently settle and permanently lock into place without generating any internal stress. And finally, Section 5. Polishing to perfection. Reaching nanometer precision.
So, our glass has survived the literal fire, it survived the months of agonizingly slow cooling, and it successfully shed 20 tons of mold. But the hardest part? It's just getting started. To turn this raw, curved slab of glass into a highly sensitive, scientific instrument capable of seeing the dawn of time, it has to be polished, and that takes 18 long months. For a year and a half, massive machines using diamond tools physically grind away up to 2,000 pounds of glass from the surface. And as they grind, they are constantly testing the optical shape by bouncing laser beams off the surface to catch even the tiniest microscopic flaws.
When that polishing is finally wrapped up, the shape of the mirror is accurate to about 1/1000th of an inch. To put that in perspective, that's roughly 1/4 the thickness of a standard piece of paper. It's completely wild. This gives these massive 26-foot wide Earth-based mirrors a nanometer-level precision that rivals, and in some cases even beats, the legendary Hubble Space Telescope. When you zoom out and look at the whole timeline of the mirror's journey, the contrast is staggering. You spend a few days carefully loading raw chunks of glass into the mold. The actual melting phase at 1200 degrees, that only takes a matter of hours. But the finishing phases, the 3 months of delicate annealing to lock the atoms, and the 18 months of meticulous nanometer-level polishing take nearly 2 entire years. It is a literal marathon of precision engineering.
Which leaves us with this beautiful, really profound thought to wrap up today's explainer. When you really get down to it, we are using the most fundamental, ancient arts of humanity, packing molds, melting materials in a fiery furnace, letting them cool, and polishing them by hand. But today, we're taking modern robotics, lasers, and mathematics, and pushing those ancient crafts to the absolute limits of physics. And by doing that, we create a perfectly curved window that lets us look past our own tiny world, deep into the grand vistas of space, all the way back to the very beginning of the universe itself. What an absolutely fascinating journey. Thank you so much for exploring this with me today, and hey, keep looking up.